I will. Go ahead.
Okay, so the first thing we're going to talk about, like Braden said, what we did to make this review, we literally just went through your necessary skills list and said, what problem can we make about this? What problem can we make about this? So we made all these problems. So the necessary skills list is your best friend. Use it to your advantage. Everything that's on there has a chance to be tested, and you're not going to be tested about anything that's not on there. So make sure you check that out. Okay? So the first problem that I wrote up is a simple concentration problem. Okay, we've dealt a lot about concentrations. So, you mix 63 milligrams of sodium sulfate with 1.4 kilograms of water. What's the molarity of the solution? Okay? So, think about this for a second. I'll give you a few seconds to think about how you do it. And then for the sake of time, we're probably just going to have to, I'm just going to have to jump into the solutions because we have a lot of material to cover in an hour.
Stand close to the wall.
Is it valid now?
I think so. It's fine. The angle is up, but it's like it's got your head and all the stuff on it. So I think it's fine.
Okay, so let's go through it. The first thing that might have glitched you if you're reading this problem is that we have no volume in liters, right? We're talking about kilograms of water. This is one thing that you should have memorized in 105. If you don't have it memorized, memorize it now. The density of water, okay? The density of water is 1 gram per milliliter. And with that being said, it's also 1 kilogram per liter, okay? So I wrote this out here like this on purpose. 1.4 kilograms of water. That could have thrown you off. If you knew the density of water, you would just know, okay, that's just 1.4 liters. So don't get tripped up on things like that. Memorize the density of water, okay? Second thing that you see in this is our solute, we have it in milligrams. And we know for molarity, it needs to be in moles per liter, okay? So the first thing I'm going to do is do dimensional analysis to find out how many moles I have here in 63 milligrams of sodium sulfate, okay? So starting out, just start out with your given. 63 milligrams of sodium sulfate, and I want to convert this into grams, okay? So there's 1 gram for every 1,000 milligrams. And then we can convert that to moles. There's 1 mole of sodium sulfate, and the molar mass is 142 grams. Okay? So our grams cancel, our milligrams cancel. We're left in moles of sodium sulfate. And if you did that, you should have got 4.44 times 10 to the negative 4th moles. Okay? Now, like we talked about, the density of water, 1.4 kilograms of water is just 1.4 liters. So now we just take that value, divide it by 1.4 liters, and you get your molarity. And it should be 3.2 times 10 to the negative 4th. So that is a really simple concentration problem. You need to be able to work through those units. Yes?
Isn't it over liters of solution? So when you add the sodium sulfate to the water, in order to get the whole liter of solution?
Good, yeah. I'm neglecting usually they neglect the solute that you add. Unless they give you a density for it, then you can calculate the volume for it.
Okay.
But in this case, I'm just neglecting the extra volume that my solute would add.
Okay, so
But
you
good
just
question.
solve it pretty much.
Yeah, usually it's just like that. Good question though. Any other questions on this right here? Concentration. Okay? So let's move on. The next thing I want to talk about is conductivity and ions and what makes a solution conductive. Okay? So who can explain what makes something conductive? Ions, okay? Good. So the more ions, the more charge I have in my solution, the more conductive that thing is going to be, okay? So I wrote up an example problem here, and I want you to find which of these following solutions is most conductive. Okay, another way to word that is which of the following solutions is going to produce the most amount of moles of charge, or the most amount of moles of ions. Okay? So, you should be able to eye this pretty simply. Okay? So all we have to do is first we have to analyze each of these salts that we're given and find out what ions they're going to break up into. Okay? So calcium chloride is going to break up, when we put it in water, into a calcium ion and a chloride ion. Okay? So there's 2 moles of ions for every 1 mole of calcium chloride. So what I can do is just take that concentration, multiply it by the number of moles of ions formed, and just get a number. Okay? And that number is, then I can rank all these based on that number and figure out which one's going to be the most conductive. Okay? So 1.5 molar times 2 moles of ions is just going to be 3. Okay? Or we can say 3 moles of ions produced, assuming we're in 1 liter. Okay, next one. 1.7 molar NaBr. NaBr is going to break up into a sodium and a bromide. Okay? So 1.7 molar times 2 moles of ions produced is going to give us 3.4. Yeah. Okay? Now, calcium bromide is going to be a little bit different than the first two. It's going to break up into 3 ions. Okay? We're going to have a calcium 2+ ion and 2 bromide ions. So, to figure out the value for this one, I take the concentration of it, multiply it by the number of ions that are produced, and in this case we get 3.9. And the very last one, 3.5 molar glucose. Glucose is a non-electrolyte, meaning it does not break up into ions. So if you put glucose in water, it's just going to stay as glucose. So my number that I'd get, it would be 3.5 times 1, because it's not going to do anything, and you'd get 3.5. So now looking at these values, you can see that this 1.3 molar solution of calcium bromide would be the most conductive. So one thing to not get tripped up on is don't just look at the one that has the highest concentration, because if you would have done that, you would have picked glucose, okay? So you have to take in the concentration and the number of moles of ions that that salt is going to dissociate into. Yes?
Is glucose more conductive than sodium bromide?
No.
No. Okay, so it's not.
Well, in this case, I wrote it in this case just to teach you that concentration rule, to not look at the concentration. I'm not sure exactly, but I'd definitely say sodium bromide is more conductive because it produces ions. Yes?
What else could be considered a non-electrolyte?
A non-electrolyte is anything that's not a salt. So anything that's not an ionic compound. So if there's a metal and a non-metal forming an ionic compound, that's a salt. It is an electrolyte. Anything other than that is a non-electrolyte. Good question. Yeah?
With the greater charge give stronger electrolyte? So like for example, if NaBr gave us 3.9 moles of ions compared to the calcium bromide, because the calcium is a 2+ charge, does that make a difference?
Yes. So if you're doing these problems, and I'm not sure if it's going to get this complicated, but if you're doing these problems and you get to the point where you get the same number out here, then what you want to look for is the charge that's there. So an ion that has a 2+ charge or an ion that has a 2- charge would be more conductive than an ion with a 1+ or a 1-. Good question. So you can usually solve them just by doing the number of moles. If he's really trying to trip you up, then revert back to the charge that's on the ion. If a greater charge is going to produce a stronger electrolyte. Okay, any questions on this? Okay, let's move on. Will you raise my board up? A little bit more. Okay, so next thing we're going to go over is Hess's law and the Born-Haber cycle. Okay? Now, for these, it's important that you guys understand some different enthalpy values. Okay? These are on the necessary skills list. So, I'm just going to go through them right here, exactly what's on the necessary skills list. Okay? So, you need to know the difference between the heat of fusion, heat of vaporization, standard enthalpy of formation, standard enthalpy of reaction, and enthalpy of solution. Okay? So the heat of fusion is the enthalpy value associated with the phase change of melting or fusion. Okay? So if you remember from Chem 105, you made those heating curves where you went up and then you melted the thing and then you raised the temperature and then you boiled the thing. Okay, so the heat of fusion is that first flat line in the heating curve. It's the process of melting or fusion. Okay, fusion is when you take a liquid and make it a solid. All right, the next thing, heat of vaporization. Same thing as heat of fusion, except instead of talking about the melting, we're now talking about boiling. Okay, same exact thing. It's that second flat line on the heating curve. Standard enthalpy of formation. Okay, the standard enthalpy of formation is usually when you have when you're making an ionic compound. Okay, so we're going to have two things. We're going to make them ions, and it's kind of what we do in the Born-Haber cycle. We have two different elements, and they're going to come together to make an ionic compound, and that reaction is going to have a standard enthalpy of formation. Okay, it's the enthalpy of formation of forming that substance. Okay, and it can be whatever. It's a formation enthalpy for the reaction. Okay, standard enthalpy of reaction is like this example for our Hess's law. This is exactly what we're going to solve for. The standard enthalpy for reaction. This is not a good example, but it's when you have reactants in their molecular state or natural state. So like chlorine should be Cl2 gas, oxygen should be O2 gas, and we're forming 1 mole of products. Okay, that's the key, is reactants are in their natural standard state and we're forming 1 mole of products. And the last one, enthalpy of solution. Enthalpy of solution has to do with when we take an ionic compound and we put it in water. Okay, so say I take some salt and put that salt in water. What is that going to do? The enthalpy of solution is the heat that's either required or released for that dissociation to happen. Okay, so you guys had some of these examples in your learning suite. We talked about the difference of sodium chloride and calcium chloride. Okay, and this is one of the reasons we talked about why calcium chloride is used to melt ice on the sidewalks, is because it has a negative enthalpy of solution. Okay, so when that calcium chloride dissociates, heat is given off. So that heat can then be sucked in by the ice, which melts the ice. Okay, our standard table salt, sodium chloride, has an endothermic, meaning a positive enthalpy of solution. So when it dissociates, it actually requires heat to do that. So your surroundings would even get more cold. So if you went to go put table salt out on your ice, you would actually be doing a worse thing because the ice would be getting more cold, because that's an endothermic enthalpy of solution. Okay, so that should do it for that. Let's do a Hess's law example. So Hess's law is basically where they give you a reaction. Okay, they're going to give you whatever reaction, and then they're going to give you multiple elementary reactions, meaning reactions that help this main reaction happen, and they're going to give you delta H values for each one of these reactions. Now the idea for this is that we can manipulate these reactions in order to get to this final reaction. Okay, so we're going to have to multiply some of these reactions, we're going to have to flip some of these reactions, and it's kind of just like a puzzle. Okay, so you should never miss a Hess's law problem. Okay, because it's like a puzzle. There's only one way to do it. So what you have to do is you kind of just have to work through it, flip some things, you might have to multiply some things until you get everything to cancel out except for this final reaction. Okay, so this is the final thing we're trying to get to. Okay, so looking at this one, I'm just going to do it quickly for the sake of time. The first thing you notice here is that I have this CS2 on the left side of my final equation. Okay, now looking at my elementary reactions, the only one that has CS2 in it is this one, and it's on the right side of the arrow. So I'm going to have to flip that reaction. Okay, so I flip that reaction. When I flip that reaction, I have to flip the sign that's on the delta H. Okay, So instead of this reaction being an endothermic positive 87.9 kilojoules per mole, if I reverse the reaction, it's going to reverse the enthalpy sign. So this is now going to be negative. Okay? The second thing that you notice looking at this reaction is we have 2 SO2 here on the right, and the only other reaction that has SO2 in it is this one. It's on the right, so we're good, but we need to double it, okay? So what I'm going to do here is multiply this whole reaction by a coefficient of 2. Okay, so now I'm going to have 2S, 2O2, and 2SO2. Now again, whatever you do to the reaction, you have to do to the enthalpy. So I would end up multiplying this value by 2 as well. Okay? Now you could continue going through it. I'm just going to tell you that's all you had to do to solve this problem. So now to solve the final delta H for this reaction is you add all of these values up together. So this value plus this value doubled plus that value, and that's going to give you your final. And I think the answer, if you did it out, was negative 1075 kilojoules per mole. Yes? I'm sorry? Yeah, I didn't draw it out, but this originally was positive, so we had to flip it, so I made it a negative. Yeah. Any other questions on Hess's law? It's pretty straightforward. You just have to look at those 3 reactions you're given and make it match the first. And remember, whatever you do to your reactions, you have to do to the enthalpy signs. Okay? Any other questions on this? Okay, let's get to the buster, the Born-Haber cycle. Okay, the Born-Haber cycle is something that I remember being on an exam last year, okay? Something Braden didn't mention, we don't get to see the exams. The TAs don't get to see the exams, so we can't tell you like this is going to be on there. But I remember from last year that there was a Born-Haber cycle problem on there, okay? So, just beware. Beware and know how to do it, okay? There's also an example in the slides, a different example in the slides. So, go through it and practice it, okay? The Born-Haber cycle has a specific formula that you basically follow every single time. The whole idea of the Born-Haber cycle, and I didn't write this out, but this is our reaction. The whole idea of the Born-Haber cycle is that we're looking at a reaction and we're seeing how can we make that work, okay? So just looking at this reaction, you can see I have a solid reacting with a gas to make a solid. Now just thinking logically about it, that sounds pretty crazy. How are you going to react a solid with a gas to make another solid, right? And that's what the Born-Haber cycle is showing us, that we have these different independent steps that we have to do in order to get this whole reaction to happen, okay? Now the way these problems are usually presented is there's different enthalpy changes and different processes that you have to do in the Born-Haber cycle. And what they're pretty much always going to do is leave one of them out, okay? There's always going to be one of them left out. So, what you have to do is you have to look, let me raise this up a little. You have to look at the enthalpy of the reaction, okay? So I'm giving you this right here. This is our enthalpy of the reaction. This reaction right here has this enthalpy. That's the total enthalpy. So all of these other independent steps that I'm going to do have to equal this total number, okay? So when we get to the final step of trying to solve for this x value, I can set this equal to all of those other things summed together and solve for that x. That's pretty much always how it's presented, okay? Now we're going to go through it, the different steps. And again, the Born-Haber cycle, it's the same steps every single time. So if you know the formula and you know the steps, you should be fine. And I'm going to talk about the biggest traps that people will fall into, okay? So the first step in the Born-Haber cycle is we have a solid and we have a gas, okay? What I need to do is get both of these things into the same physical state. So what I do is I sublime that solid, okay? And that's what I gave you here, the delta H of sublimation of sodium, okay? And I told you that value was 108 kilojoules per mole. So the way I always do it, and the way you're probably going to be asked to do it, is make a little diagram like this. So it's easier to diagram as you go. For the sake of time, I just sketched it out already, but you can't just really sketch it out and then try filling it in. You have to do the process as you go, because there may be more than one ionization energy. There may be more than one electron affinity. So you kind of just have to take it as a process, okay? So the delta H of sublimation of calcium was 108 kilojoules per mole. Okay? So now what I like to do is just write out what I have. So after I sublime sodium, I'm going to have sodium gas, and I still have my half mole of chlorine gas, okay? So first step, sublime the metal. Second step is I have to break up this chlorine bond, right? You remember doing all your Lewis structures in 105. This is a Cl-Cl bond. What I have to do is I have to break that bond so I'm just working in pure atoms. Okay? So this is where we get the bond energy of Cl2. All right? So 244 kilojoules per mole. 244 right here. Half of it, right? Okay? This is one of the biggest traps that people will fall into. You have to watch out for the number of moles that you have. All of these values that you're going to be given will always be given in kilojoules per mole, okay? Now looking at what I actually have, I have half a mole of Cl2. So therefore, I have to half this enthalpy value. So the true value that I'm doing is 122 kilojoules, okay? Same thing goes for this sodium. If I were to have 2 sodiums in my reaction, I would have to sublime both moles, so therefore I'd have to multiply my sublimation enthalpy by 2. Okay, so make sure you watch out for those. Yeah. This is endothermic. Yeah, we're putting it in. So all of these reactions that we're doing going up, these are all endothermic reactions, and then the last couple are usually the exothermic ones. Okay, so I've got both of these things, and now I broke this bond. So now I have sodium gas and just chlorine. And I guess it's still gas. It doesn't. The physical states don't really matter. It's kind of weird. It's just an atom of chlorine. Okay. So now what I have to do is I have 2 atoms. The best way to make these things want to come together, and remember, my final product that I'm trying to get to is sodium chloride solid. So if I want to get these 2 things to be attracted to each other, I should make them ions. Once they're both ions, they're going to want to come together, and everything's happy. Yes?
So would you have 2 moles of chloride ions then, because you just broke them? Or is that not?
I would have if I had a whole mole. Does that make sense?
Oh,
so if I had 1 mole of Cl2, I would have produced 2 Cls. But in this case, I only had half a mole, so I ended up just producing 1 Cl.
Makes sense. Thanks.
Yep. Good question. Okay, so the next step is I'm going to ionize sodium. Okay? So if you remember from 105, ionizing is when something loses electrons. So I'm kicking an electron out of sodium. And I told you that that takes 496 kilojoules, okay? So after I ionize sodium, I'm going to be at Na plus and Cl. Okay, so I've made one of them an ion, now I have to make the other one an ion. And to make anions, we use electron affinity, okay? And one word about electron affinities, they're typically negative, except when you form 2- anions, okay? So the example that he did in class was, I think, calcium oxide. And because oxygen always forms 2- ions, there's going to be 2 electron affinities for it. Now, the reason sometimes the electron affinities come out positive for those 2- ions is because once we give an oxygen atom a negative charge, if I try and add another negative charge on it, there's going to be some repulsion there. That oxygen already has a bunch of electrons, and it doesn't really want to accept that other one. So that's why usually that second electron affinity is endothermic, and it requires energy to make it happen. So your total electron affinity could still potentially be endothermic. But typically, if you're just making one, typically it's just negative. I don't want to say always, but just look out for the values they give you. Okay? Yes?
How do you know if there's two electrons?
You'll know because it'll probably be oxygen or sulfur.
So,
Those are the main ones that form 2- ions.
on the periodic table, if it's like in the second column over, it's going to be 2,
Mm-hmm.
and it'll be 3 for the next one.
Yeah, you're probably not going to ever do that though. Yeah.
Usually the second one is positive.
Usually the second one is positive because we have to force it on because it already has a minus and we kind of have to force it. Okay?
Give us an electron affinity 1 and electron.
They will typically give you an electron affinity 1 and an electron affinity 2. Or they could give you an electron affinity 1 plus 2 and just for the whole. Okay?
Add them up.
Yeah, and then you just add both electron affinities. So if this had 2 electron affinities, I would have drawn 2 steps. So the first one might have been negative and the second one might have been positive. So if you just keep track of your thing, you'll be fine. Okay? So electron affinity for chlorine. I gave it to you. Oh, that's what we're going to solve for. Okay? So I'm not giving you this one. After I do that electron affinity, I have Na plus and Cl minus. And the last step is the lattice energy. Okay? The lattice energy is the energy that's typically released when 2 ions come together to form that ionic solid. Okay? So in this case, it was negative 787 kilojoules. So now what I want you to do is solve for this value of electron affinity. What is that electron affinity? Take a minute and try and do it out. And remember, how you solve these is each of these independent steps that we do has to be equal to the total enthalpy of reaction. Still going. Still recording. Okay, good. Now can anyone see the board? It's all tilted.
When I go, is it supposed to be tilted like because it's not, it just points out. So when I go, you're gonna have to look. So when you're standing over there, it's straight up.
It is, it's valid.
But I'd rather have it like, even if it's just switched to the side. Like,
Okay, what'd you guys get? Okay, negative 349, that's the right. Okay, so our electron affinity was negative 349 kilojoules per mole. Okay, so these Board-Haber cycles, they're pretty straightforward. It's going to be the same process every time. You're going to sublime it, and then you're going to break the bond, and then you're going to ionize it. Electron affinity, lattice energy. Yep.
I thought you used 122 for.
You did.
Because I got.
Okay, so any last questions on the Born-Haber cycle? Yeah.
So I probably just did something wrong with my equation. I got 349, but I got positive. Do you have any idea why?
You may have just missed a negative sign somewhere or something.
Okay, because I would just set negative 410 equals all the rest of it, right?
Yeah, you must have just made a calculator mistake because it's negative 349. Okay, so yes, last questions about this, and then I'm giving it to Braden. Everyone, shh, shh. I would be able to know how. I would know how to do this. Yes. Yeah, they'll probably give you these values just like this in a table or in some way in the problem, and then I don't know, you might have to diagram it or solve for it, but I would know how to do exactly like what we did here. Okay? All right, that's good. Here you go, Ray.
You can just drag it out.
Yeah.
Okay, guys, so Corbin's gone over a lot of the thermodynamic stuff, right? The Hess's law problem and things like that, and all of the different enthalpy problems that you might be asked to do, okay? A lot of that is review from Chem 105 except this Born-Haber process, but Hess's law and things like that. If you're looking for practice problems, even go back to some of your 105 material because there's a chance that it's somewhere on there, okay? So right now we're going to jump into some of the stuff with solubility. We're going to get into vapor pressure and round it out with some equations that you're going to have to use, okay? So right now we've been talking about solubility with gases, right? And so what are some of the things, when we talk about a gas going into a solution, what are some of the factors that we know affect the ability of a gas to go into a solution? Shout them out. Temperature is one of them, right? So let's talk about temperature. How does temperature affect a gas's ability to go into a liquid? Physically, like if you have an answer, like describe it, like why? Like why does it affect it that way?
The temperature of the gas or the liquid?
The temperature of just the
Like it's moving
the
around,
system,
it's like moving
right?
around quicker, so it's banging on the surface, like going in.
Right. So if we have these molecules that are moving around a lot, right, we know that temperature also affects things with vapor pressure. So if we want to get gas to go in and stay in, right, we like that temperature to be colder. So remember he was talking about the example with the nuclear power plant and with water and how they were cooling whatever they were doing with the river water, but that was heating the water up, which was bad for the fish because oxygen in the atmosphere wasn't able to dissolve or go into the water very well, so the fish weren't able to breathe, right? So temperature will affect gas's ability to go into a liquid, right, in that manner. So colder temperatures are better for the examples that we've been given in class, okay? The next part of it that affects a gas's ability to go into a solution is a little bit, I would say it's a little bit more straightforward, and that's just the partial pressure of the gas above that liquid has to be high, right? So if we have a lot of that gas above a liquid and the partial pressure of that gas is high, its chances of going in are greater, right? And that just makes sense. So one of the differences that I just wanted to make very clear, when we talk about a gas going into a solution versus vapor pressure, which we're going to get to, which is also, you could say, gas particles above a solution, is when we talk about solubility of gases, we're taking a gas and putting it into something different than itself, right? Vapor pressure, we're looking at some sort of solution and how its own molecules, how much are above, right? But this, we're talking about like putting CO2 into water, something like that, right? We give that a name, and it's called Henry's Law. So put Henry's Law in your equation box, all right? And we're going to look at this problem, right? This is a classic problem of a Henry's Law problem in solubility of gases. How many grams of CO2 gas are dissolved in 1.5 liters of water if the partial pressure, so I abbreviated a lot of stuff in some of these problems just to make them quicker, PP, right? Partial pressure of the gas is 2.4 atm, okay? And then they give me some random information with this problem, right? The KH of CO2 in water was 3.4 times 10 to the negative 2, and these were the units. So when I want to solve a problem like that, Henry's Law, what's nice about it is it's literally a plug and chug. And a lot of Chemistry 106 is like that. So I look at my equation. Let's just describe what these variables are. This is how much moles of gas are in that volume of liquid, right? This is the concentration of the gas. Usually what we're solving for is equal to some constant that's given to me, or maybe I'm giving everything else and asked to solve for that. But usually that one's given to me in a table or just flat out in the question stem, times the partial pressure of the gas, right? In this problem, we made it simple because I flat out gave you the partial pressure. But the only spin that I could see in a problem with Henry's Law is they would tell you what a total pressure was in some sort of situation, be it some sort of system. It could be a closed container, open container, just the atmosphere. They would tell you the total pressure and then maybe like the percentage of the gas you're looking at what its percent of the total would be or something like that, right? It would be up to you to solve for what the actual partial pressure or contribution to the total pressure that gas is giving, right? So that's the only curveball I can see being thrown in a problem like this, okay? So when we do this, we're going to solve for this. So we're going to say we want that. We know what the KH is, right? 3.4 times 10 to the negative 2. I'm going to leave out the units, but I wrote the units right over there, okay? Times the partial pressure. And when I do that, I should get what the concentration of that gas is. Okay? And let me make sure I did it. This is what we would get. Okay? Moles per liter. So, are we done? Do we know the concentration of the gas? Are we done? No. Why are we not done? I specifically wanted to know grams of CO2 that were dissolved in this solution, right? So I need to get to grams. Also, this is a concentration, right, in just moles per 1 liter. But I look at my problem, and I'm specifically asked about a 1.5 liter solution, right? So I need to convert this. So I take what I have, and I'm sorry I'm writing a little bit small, but this will be recorded so you can see this a little bit better, right? This is moles over 1 liter. And then I just do dimensional analysis like you've done a lot in Chem 105. I know that I have 1.5 liters, right? And so that those units will cancel. And then I'm just given moles, right? If I know how many moles are going to be in there, I can take moles the rest of the way to grams, right? And that's stuff you guys have done a lot. So these problems are not that difficult. The only curveball I can see is having you solve for the partial pressure and maybe understanding some of the conceptual things about how a gas would go into a solution, right? Colder temperature, and most importantly, a really high partial pressure to go in that. Okay? Is there a question?
Yeah, so partial pressure would be mole fraction times the total.
So if you're, yeah, exactly. So if you're not familiar with how to get to the partial pressure, again, there are a lot of ways to solve it. It depends on what you're given. The most standard way is you would take the mole fraction of the gas you're looking at and multiply that by the pressure total of your situation, right? And so if that is confusing to you, let's talk after the review, and we'll go over how to do stuff like that. Just because there are bigger, more important problems to get to. But that is a good one. You do need to know how to do that.
Okay, this one's really quick. Now, is this statement true or false? The partial pressure must be more than the vapor pressure?
So,
or the gas to stay in there and get more of it in there. Vapor pressure is when it's trying to bust out, right?
yeah. So when we get to vapor pressure, we'll address some situations that might be like that, okay? All right. Okay, so we're going to move on from this. All right. Okay. So now let's talk about vapor pressure. So I noticed on the necessary skills list, what Dr. Macedoni said was just like, know vapor pressure. It wasn't even like, know this or know that. It was like, just know the phenomenon of vapor pressure. So what that means is you kind of got to know the ins and outs of anything related to vapor pressure, okay? So that could mean there might be problems in a style of problem we haven't seen that you could potentially be asked, but it should be similar enough where you can solve it if you understand conceptually what vapor pressure is. Okay, so let's go over in our minds, what the heck is vapor pressure? Let's describe it. A lot of you probably already have it down studying for the exam, but let's get it as a group so we conceptually understand what it is so we can answer difficult questions. What is vapor pressure?
I know that it's an indicator of the volatility of a liquid.
So he says it's an indicator of the volatility of a liquid. So we now have another term that we might not know, volatility. So who can expand on that? That vapor pressure is an indicator of the volatility of a liquid, and how? How are those two things related? Is one big, it makes the other one small? How does that work?
So what that means really is that, when you have like molecules of a liquid, how easily like one of them will like come off the surface because of the the
intermolecular forces.
There you go, intermolecular forces between
It's good.
the molecules below it, and like kinetic energy that's like kind of bouncing and jostling around, and another one will pop off. And so the higher the volatility, the higher the vapor pressure.
Right. Right. If something is volatile, it evaporates easily. Right? And so if something evaporates easily, it's going from a liquid phase to a gas phase pretty easily, right? And so if it's really volatile, then you would imagine the vapor pressure to be higher. So let's look at a picture that I've drawn, and people in my recitation have gotten kind of this similar spiel before, but it's a little different of the problem we're going to do. So this is our closed container, right? Here we go here. We have our solution, right? We're going to look at how many molecules of this solution, of this liquid, are able to escape into the gas form even well before I'm boiling it, right? Because I know if I heat it up enough to boil, then they're all going to be doing that. But that's not the point of vapor pressure. Vapor pressure is at any temperature, there will be a few of those molecules that are able to escape from the liquid phase into the gas phase. And when we say escape, it's a lot like what he said down here. Obviously, those molecules on the surface, so the ones that are up here, right? There is something specific that they have to overcome, right? They're locked in together, right? They're a type of interaction with the other molecules around it that are holding it down. And if it has enough energy, enough kinetic energy and movement that it can bust those bonds, then it'll escape and it'll go into the atmosphere here. And so if we measure the pressure of the molecules above, right, that's the vapor pressure. And so the thing about vapor pressure, it's not constant. I can't say water always has this vapor pressure. I can say water at a specific temperature would have such and such vapor pressure, because whatever is determining what's holding these molecules down is continually changing, right? If it's getting hotter and hotter and I'm adding more heat, then I'm continually disrupting the interaction between the two molecules here, or those intermolecular forces, and causing more of those molecules to shoot into the atmosphere, right? So I start to conceptually understand, okay, vapor pressure is determined, right, a lot by temperature. If the temperature is high, I'm giving those molecules more energy to be able to escape. And the second thing is, if I have molecules that are attracted to one another pretty strong, it'll also be harder, right? So one of the things is, or what, I guess, having said that, what are the two things then, rock solid, that affect vapor pressure? Temperature and intermolecular forces. So you can probably expect to solve some type of problem, either mathematically, using the equation we're going to talk about in 2 seconds, dealing with vapor pressure, or just a conceptual question, right? So with vapor pressure, and having talked about kind of what it is and the intermolecular forces involved, right? And by the way, if I say intermolecular force and you're like, okay, what are intermolecular forces? And like you're trying to remember the list and how they work, that is kind of one of the things that should probably go on this list, because it's just a big 105, huge section 105. So we're not going to jump into like each and every one. We'll graze them as we look at this. But if you don't know that well, I would mark it as something you should get ready for this exam. Be prepared to know that, because it'll be through the rest of Chem 106 most likely, okay? So when I mathematically want to solve for vapor pressure changes, this is my equation, right? I don't want to, who can pronounce, like it's the Clausius-Clapeyron, what is it, Corbin? How do you say that one? I hate saying that one. I don't know. Yeah, whatever it is. I hate that name. But this is the equation you need to know, okay? Now, when we look at this equation, I'm just going to already mark off some of the biggest mistakes that are made using this equation, okay? Big mistake is, it is important, right, how I order these two temperatures and how their vapor pressures according to these two temperatures and where they are here. Okay, so make sure you you can't just throw them together however you want. That order is important. The other thing is, when I deal with this delta H of vape, right, of vaporization, that value is almost always given to me in kilojoules per mole, right? But underneath, we're dividing by the R constant, and the one that we are most familiar with is 8.314, which is in joules, okay? So a big mistake as you're going quick is you leave this in kilojoules and divide by joules, right? Which your answer will be wrong. So make sure, what I would do is just put that into joules, right? Just put that into joules, that's how I would always do it, and then solve it through. The next problem, these temperatures, I've got to do that in Kelvin, okay? Has to be in Kelvin. If you're confused on how to go between Celsius and Kelvin, mark that on your paper and look that one up. That's also a bit of a 105 review, okay? So that's the equation you should know. Let's jump into this conceptual problem with vapor pressure and intermolecular forces and things like that. We might... Oh, right, and Corbin brings up a good point. Yeah, vapor pressure in torr, not ATM. Glad he said that. Vapor pressure in torr and not ATM for this section, okay? We might skip a couple problems because of time, but this is an important one right here. So, if you can conceptually understand vapor pressure, you can answer a question like this. First of all, vapor pressure is important. I'll get you in just 1 second. Vapor pressure is important, you guys, because if I can get the vapor pressure of whatever solution I'm dealing with to equal whatever the atmospheric pressure is at that moment, that solution will start to boil immediately, right? So if I took a solution and I put it in a perfect vacuum and I sucked out all of the atmosphere around it, right? So that the pressure inside the vacuum was 0. Would the solution start to boil? Yes, right? Even if I didn't add any heat, I just sucked out whatever the pressure was around it, it would start to boil if the pressure was 0, right? As soon as the vapor pressure is equal to the atmospheric pressure, that's when it happens. And so that's important to know, because understanding the factors that affect vapor pressure, we can look at the factors then that would affect boiling point and things that would start to boil first. Yeah.
So earlier you said pressure in torr, but wouldn't it not matter because you're dividing pressure by pressure?
I would do it in torr just because a lot of the problems are in torr, and I don't think it would matter because you are just dividing. Yeah, I don't think it would matter. But I would do it in torr.
I would always do this one because if you're trying to solve for something that's on the right side of the equation, you're going to cancel the natural log out and then end up multiplying one of the pressures. And if you have it in ATNs, you're going to multiply a much lower number than should be multiplied. So it might end up being valid, but
I would just
it's always done in torr.
It's always done in torr. Just do it in torr. Yeah. Okay. So let's look at this. Okay. So if I asked you to rank A, B, and C, and D from who will boil first to who will boil last, you should be able to do that with a little bit of Chem 105 knowledge and understanding what affects vapor pressure. So as we look at this, remember, vapor pressure is affected with temperature and intermolecular forces. So if I want to pick the one that's going to boil first, it's going to be whatever molecule here has the weakest intermolecular force, right? So we need to immediately look at them and label them as what's their strongest intermolecular force, okay? As I look at this, right, carbon dioxide, here's the Lewis structure, okay? What is the strongest intermolecular force? Is this an ion? No, right? Is it polar? No. So it can only be nonpolar, and its strongest intermolecular force is London dispersion, right? Which is the weakest. So right off the bat, we're thinking that's probably my weakest one. Okay. Is this an ion? No. Is it polar? Yes. Can a hydrogen bond? Yes, right? So we would say hydrogen bonding strongest for that. That's a pretty strong one. Let's look at this one. Polar? Yes. Ion? No. Can a hydrogen bond? Yes. Okay, so these two can hydrogen bond. Now we got a bit of a standoff. Water, we know can hydrogen bond, right? Water we deal with a lot. So immediately we say the one that will boil first is going to be carbon dioxide, okay? So I'm going to put A down. Carbon dioxide is going to boil first. Its vapor pressure would be the highest at the lowest temperature, and so it would boil first. Now let's look at the rest of these. How can we determine if all of them can do hydrogen bonding, right? How can you, as a chemist, figure out, without looking something up, which one would boil next? Because they can all do hydrogen bonding, but let's get more specific. Who can hydrogen bond even better, right? Who can hydrogen bond better between these two? Water. Why can a hydrogen bond better? Because it has more hydrogens available to make that hydrogen bond, so there are a little bit more grip on each of the molecules around it. So immediately we would say, okay, we know water's going to be better than this one, so this one's looking like it might be the next one, but let's compare this to that. Who can hydrogen bond better? It's about the same, right? But what other factor would affect the boiling point or intermolecular force differences between these two? Surface area. The size of this one is so much bigger that its London dispersion forces would overcome and be stronger, right, than this one. So we will say C is our next one, right? And then a standoff between the cyclohexanol and water. What we've got here is, okay, we think this one can hydrogen bond a little bit better, but I specifically drew a 6-membered ring, which we've talked about. That's kind of the threshold where London dispersion becomes stronger than a lot of those hydrogen bonds. So actually, this is your strongest, right? So water would go next, and then this. It's important to look at those intermolecular forces and be able to determine and answer those types of questions, okay? All right. So look at this really quick. If I was solving a problem, what is the vapor pressure of ethanol at 50 degrees, right? With the information that's given here, I couldn't solve the problem yet. I don't have enough things. But if I told you what the boiling point of ethanol was, you have enough information immediately to solve for what the vapor pressure is at a different temperature. So if I told you that the boiling point was 78.37 degrees Celsius, you immediately have enough information to be able to solve what the vapor pressure is of ethanol then at 50. Because we could say, okay, we know that the vapor pressure at its boiling point is equal to atmospheric pressure. They don't tell you what pressure you're at in atmospheres, you assume 760 torr, right? So then you would know both temperature values, right? You would know one of the vapor pressures, you always know those, and you would just have one thing you didn't know, one variable. and you could solve for that. And we don't have time to do that problem. I'll write the answer on the board really quick. It is 238.4 torque. So as you're rewatching this, you can do it. Oh, you need that too. I'm sorry, guys. Yeah, that's usually given. My bad. Okay, where did I put that? Okay. Yes, you're given that too. Thank you. You're given that too. Okay. You can choose. Just assign it and keep the pattern the same.
How do we know if normal blind point is T1 or T2?
You can choose. Just keep the patterns the same. If you do this, one is T1, make sure that's the value over here. Just the pattern is what is important. Okay? So, the last thing I'm going to talk about, we have 5 minutes and then Corbin's going to go over something, is this. Deviations in route law. Okay? So Raoult's law, again, is a equation that's dealing with vapor pressure. But it's vapor pressure now when I have a solution and several things mixed into that solution. So it's not a pure solution, okay? And how Raoult's law works is if I want to find out the vapor pressure of my solution, that is going to be equal to the mole fraction of one of the pieces that I'm putting in my solution, right? The mole fraction, times the vapor pressure when it's all alone, when it's just in its pure form, right? So that's going to go together, and I'm just going to add up the mole fraction for something else that might be in there, times its vapor pressure when it's by itself, and so on and so forth. So it's not a difficult problem. It just, you need to make sure that you plug these values in correctly, right? So, a question like this, what is the vapor pressure when 0.685 moles of hexane is added to 0.564 moles of benzene? So I have two different things, I'm adding them together. I want to know the vapor pressure, so I have a mixture here. It's not a pure solution. But I'm given the values that I need to know. I know that the vapor pressure of hexane when it's pure is this much torr, and the vapor pressure of benzene when it's pure is that many torr, okay? So using Raoult's law, I already know the vapor pressures when those two are pure. I just need to solve for what their mole fractions are. And to get a mole fraction, I'm going to take the amount of moles of hexane that I have for hexane, 0.685, and divide it by the moles of hexane added to the moles of benzene, so the total, so 1.25, roughly, okay, moles. And when I do that math, that is the mole fraction, okay, that's how we do that. So you'll just plug that through, and you're able to get what the vapor pressure total is, okay? That's how you solve a Raoult's law problem. So, jumping into some of this that's important, deviations from Raoult's law with vapor pressure, it's more of a conceptual understanding. If I take two things, and by themselves they have some specific intermolecular force, right? And I give it a strength. When I mix them together, all of a sudden, the intermolecular forces together are way weaker than they were when they were alone. There will be a deviation from just a specific Raoult's law, like something simple with an equation. And what happens is, if I put two things together and the forces between them are weaker than they were when they were just alone, right? The deviation is that the vapor pressure will increase, right, like this. So instead of, you guys have seen these in Dr. Macedoni's slides, this is just a sketch. So I'm not, the X and Y axis and stuff, it's all in Dr. Macedoni's slides. But specifically, it makes sense, right? If I get weaker intermolecular forces when I put them together, they'll escape into a gas phase easier, so a vapor pressure would be higher. So you would see a positive deviation like in the vapor pressure lines right here, right? Everything would be a positive above where the dotted line is. And if they were stronger all of a sudden when I put them together, you would get a negative deviation. So you would get something that's now harder to escape into the gas phase, so the vapor pressure would be lower, right? So below these dotted lines, you would see the real lines, okay? Those are just conceptual deviations when I look at intermolecular forces. So again, you're seeing intermolecular forces. It's way important to have those things down. And that's basically everything for me. Do you have anything to end with, Corb, while I'm answering your question?
So is there a way to know whether it's going to be weaker or stronger when you put them together?
So if you look at the intermolecular force that's given, so for instance, if something pure by itself will hydrogen bond with itself, and then you put something new into it that will disrupt the amount of hydrogen bonds it can do, because the new thing cannot hydrogen bond, right? All of a sudden, the overall solution is weaker as a whole than they were when they were just alone, right? So that would be an example of a weak deviation. Okay.
Yeah. Okay, we're gonna go a couple minutes over, but I think it's gonna
If
be
you
worth.
need to take off, just try to be quiet. when
I
you
would,
go.
yeah. It's kind of distracting, so if you can stick out like 5 to 10 more minutes, I really think it's gonna be worth your time. Okay. So the next couple problems that we're gonna go over have to do with colligative properties. And so let's just bust right into it. Okay, so we've talked about how when we add, Braden was talking about how when we add a solute, there's different things that can happen to the vapor pressure, right? There's also things that happen to the boiling points and the freezing points, okay? So the two things that I want you to lock into your head when you add a solute to a solvent, there's two things to happen with colligative properties. Freezing point depression, boiling point elevation, okay? Boiling point elevation, freezing point depression. That will always be the case, okay? So, the equations, if you want to put it in your little equation box that you're going to use, are it's delta T equals I. So if this is for boiling, and then they're going to give you a Kb value times molality, okay? And then for freezing, it's going to be delta T equals I Kf times N, okay? So those are the two equations you're going to use. Now, I want to go ahead and do this problem, okay? So, which has the largest boiling point elevation, okay? 0.55 molal sodium sulfate, 0.73 molal potassium bromide, or 1.2 molal glucose, okay? Does everyone remember what the I value is? Okay? The Van't Hoff factor. The Van't Hoff factor is the number of ions that your salt is going to break into, okay? So for example, potassium bromide breaks up into 2 ions. The I value here is 2, okay? Now, for the sake of time, when you go back and watch the video, pause the video and do this on your own. But the answer is, let's see where I wrote this. The answer is this one right here. Okay? So this one had a temperature change of 0.85 degrees Celsius. Okay, so one thing to watch out for when you're doing these, don't just choose the one with the largest molality value, okay? Obviously, glucose has a way higher molality than this sodium sulfate, but you have to take in the Van't Hoff factor, okay? That's why this one ends up getting a higher change in boiling point. Okay, this last one is pretty similar to one that you had on your smoke. Is there any questions on this?
What are the KBs?
Oh, I didn't give you the KBs. Thank you. Okay, so the KB of water is 0.512. Yeah. Just solve for the exact value of temperature change you need it, because you plug it in here for both of them. But yeah.
Are we going to need to know the difference between ideal versus in reality for the Van't Hoff factor?
Okay, that's a point to bring up. You're not going to have to memorize those ideal values, but what they might have you do is solve for the true I value. Okay, so what he's talking about is one that I know is sodium chloride. We would say this has a Van't Hoff factor of 2. Okay, just qualitatively looking at it, this is going to break up into 2 ions. Now, in reality, not every single ionic compound is going to break up when we put it in water. Okay, there's going to be some that still stick together. So that's why they've experimentally gone through and they found specifically for sodium chloride, the Van't Hoff factor is 1.9. So that tells you theoretically it should be 2 because it breaks into 2 ions, but not every single one is going to break up, so it's 1.9. And he has those tables in his slides, so you can just breeze through those, but you're not going to have to memorize those values. If you're not given the true I Van't Hoff factor for your compound, just use the theoretical. Yes?
So is your KB always for the solvent?
Yes. Yep. Yep. Any other questions on this one? Okay. Let's do this problem, okay? This one, in lecture, you have that big, huge thing about solving the molar mass, like these crazy canceling the units out and stuff. I thought it was kind of, like me personally, I thought it was kind of difficult to understand. Maybe you guys are algebra wizards and you just got it right on the first try. So I want to do a problem that's very similar to that, and just a little bit of a different way, the way that I've always done it. You might end up liking this better. You might end up liking the way on the slides better. Whatever works for you, use it, okay? But I'm going to go through the way that I've always done it, okay? So, reading the problem. You add 126 grams of Tylenol. By the way, I've just made this problem up. It's not. We're not going to solve for the true molar mass of Tylenol. I just wanted to have some kind of drug in there. That's narcotic. Okay. So we had 126 grams of Tylenol. Thinking about how you can use chemistry in your everyday life. Okay. To 75 milliliters of water. Okay. And the kb for water is here. You increase the boiling point by 1.7 degrees Celsius. What is the molar mass of Tylenol? Okay, so first of all, just thinking, molar mass is grams per mole. Okay, so the first thing I'm going to want to do is, I have these different things. Now, anytime you see a chemistry problem, you should immediately look through what values you're given. Okay, so if I were reading this problem, I would say, okay, I'm given grams, I'm given a volume, oh, I'm given a kb. I'm probably going to use this equation. Okay, so there's going to be something that hints you towards an equation to use. So analyze what you're doing. We're talking about boiling point elevation, so we're going to end up using this equation. Next thing you want to do is find out which variable they didn't give you, okay? In this case, Tylenol, oh, and I was supposed to write in there that it's a non-electrolyte. It's not going to dissociate into ions, okay? And so you know the I value is just 1. I should have added that in there. We're given the kb. We're given the temperature change. We're not given the molality, okay? So that's a good place to start. Let's solve for the molality. So you set it up in the equation. So 1.7 degrees Celsius is going to equal 1 is our I value times 0.512 times x. And let me see where I wrote this. And your molality that you solve for should be 3.32. Okay? So now, remember where we're trying to get here. We're trying to get to grams per mole, all right? Now, looking back at my equation, I have a volume, right? I was given a volume. But I wasn't given how many moles of solute I added. I was only given how many grams of solute I added. So the next thing I can do is just you can just set up the molality equation. You could have made a fraction here with your x. That works too. This is just an easier way to think about it. So we set up our molality equation, and then we solve for the unknown variable. In this case, it's the moles of solute, okay? So remember, molality equals moles of solute over kilograms of solvent. Okay? So, the next thing I have to do is convert my solvent, which is in milliliters. It's water. I know the density of water, so I can find it in kilograms, okay? So it's going to end up being, I think it's 0.075 kilograms, yeah. So converting milliliters to kilograms with your dimensional analysis, you're going to get 0.075 kilograms. And this molality we solved for was 3.32. So now you solve for moles of solute, okay? When you do that, you should get 0.294 moles. Okay? So now, what's the end goal? What? Oh, 249, sorry. I'm gonna write it up here. Okay, so our moles of solute was 0.249 moles. Okay? So now, think about what I just solved for. I just solved for how many moles of solute I added. I also know how many grams of solute I added. So what I can do is just do grams divided by moles, and that gives you a molar mass. So I would take, sorry if this is a little bit hard for you guys, but I would take this gram amount that they gave me and divide it by the mole amount that I solved for. So 126 grams divided by 0.249 moles, and you should get a molar mass of 506 grams per mole. Okay, that's a huge thing. I just made this problem up, so it's not real. Yeah.
None of the
Be
stuff
a
we
big
use.
Tylenol pill. Okay, any questions on this right here? So work through the unknowns, and then remember, if you want a molar mass, just divide the grams by the moles. Okay?
And you guys, good luck on your exam. And you can watch this video. We're gonna get it up tomorrow. And if you have questions, don't just take off. Stay, and we'll work through things together right here for the next 15 minutes or
Yeah,
so,
like
or whatever.
10 minutes.
We'll stay until you feel pretty comfortable. Okay.